transformer utilization factor. Now from the name itself, it is clear that what actually this factor is trying to find. Basically we know that these terms we will be using whenever we are using transformer everywhere. Especially we are talking here in relation with the rectifiers. So we know that this is one circuit for the half wave rectifier. Here what we did, we utilize this transformer, and we know that why we are using the transformer, we have to convert the high value of input into the value which can be handled by this circuit like diode and resistor. So generally here it will be a step down transformer. In the same manner there can be another type of transformer also. So with this factor, transformer utilization factor, we will be finding out how much this transformer is utilized, and we will calculate it in terms of percentage, right? This diagram I will be utilizing for calculating the TUF in case of half wave rectifier. This derivation we have already covered in some another lecture, that's why we are only interested in this diagram here. Okay, so now first of all let me tell you the definition of the transformer utilization factor. So from the name itself it is clear that what it can be, but still here I have written everything to save the time. The TUF is defined as the ratio of the DC power delivered to the load to the AC power rating of the transformer. Now why DC and why AC? We know that here we are talking in respective of the rectifier. So we know we are utilizing the rectifier to convert AC into DC. So in this way it is nothing but the ratio of how much power, means how much DC power delivered to the load divided by what is the rating of this transformer here. So in this way the ratio or the equation for the TUF can be written like this. Here it is. So we can write the equation TUF is equal to DC power delivered to the load. Now I have shown you in the diagram, divided by AC power rating of that transformer. So in that way the equation becomes PDC by PAC. If you remember, similar kind of equation we have used at the time of calculating the efficiency, where we had the equation for efficiency is the output DC power divided by AC power, right? But here only the thing is that here we are using the AC rating of the transformer. That is the only difference, and accordingly what change occurs, that we'll see. Now we'll see one by one. First of all let us go for the half wave rectifier. Now in half wave rectifier there is an interesting fact. The minor difference which all should note is here, like directly I will show you. In case of half wave rectifier, according to the theory of transformer, the rated voltage rating of the secondary will be Vm by root 2. This I am talking about the AC, because here we are interested in AC power rating, no? So that's why this is the RMS value of the voltage, and it is given a Vm by root 2 in half wave rectifier also. This point I am pointing out because you should not be getting confused. So Vrms for the secondary will be Vm by root 2, as it is purely sinusoidal. I will explain it once again once I read out this all thing. While the current of half wave sinusoidal, while the current is half sinusoidal in case of half wave rectifier, hence its RMS value is Im by 2. I think this we have already derived, right? In case of half wave rectifier, the RMS value of the current is Im by 2, that we all know. Now let us try to understand this thing with the help of diagram also. Now what I mean to say is that here you can see in the diagram, if this is the output, now in order for this current to flow, we know that this has to flow through this complete circuit. It means it will flow through the secondary winding also. It means that only for the half of this cycle the current is flowing, right? And that's why we have derived for the same also, that IRMS we have got there, that is Im by 2, right? But whenever we talk about the voltage, so here we can see whether it's a positive half cycle or negative half cycle, the voltage will be always here, and that's why we have to consider it even if there is current is not flowing, right? So somebody may have the question, if the current we are considering, means if we are writing voltage here Vm by root 2, or we are not considering the current, then why in case of IRMS we have made a different thing? The thing is that whenever the diode is reverse bias, at that time here all voltage is blocked by the diode, and at that time no voltage is available across the load. और इससे पहले जो हम लोगों ने इक्वेशन देखा था उसमें हम लोगों ने आई आर एम एस इन थ्रू द लोड करंट देखा था. सो वंस अगेन आई एम रिपीटिंग, whenever we are talking about this load resistance, at that time we consider the here voltage 0. But if in this case we are talking about the secondary voltage, so even during the negative half cycle here minus voltage is there in the secondary, right? But here it is 0. So I think it is clear, and if it's not clear, then I have written it everything, that in case of the this particular equation we should be considering the RMS value of voltage to be Vm by root 2 and RMS value of the current to be Im by 2. With this assumption, let us start our equation. Actually we have consumed lot much time, but still it was necessary to cover. Now let us go for the our required equation. So here again we are interested in PDC and PAC. So this we will write PDC. Now we know PDC is given by I square into R. So whenever we talk about the DC, we'll be using the IDC, and this equation means IDC square into RL. Now we have the equation of IDC in case of half wave rectifier, and it is given by Im by pi. So it is Im by pi and its square, and this thing will be multiplied by resistance RL. So this is the value for this PDC. In the same manner, let us go for PAC. So now we know that I will write here. Okay, so PAC, that is nothing but V into R. V into means voltage into current. So it is VRMS multiplied by IRMS. And for this the everything is I have written, right? So here what I will be putting, VRMS is Vm by root 2, IRMS is Im by 2. So when I put this, I am getting it Vm by root 2 and it is multiplied by Im by 2. Is it okay now? Now we know that in case of half wave rectifier we had some equation for this Vm also in terms of Im. So if you do not remember, let us see this diagram. In this diagram again we know the Im flows like this, and what are the different resistance which are coming? Rs, resistance of diode, and resistance of this load. And that's why what I can write here, Vm can be written like Vm is equal to Im multiplied by all the resistors Rs plus Rf plus Rl, right? But let's neglect, as we do already, Rs and Rf, Rs and Rf. So if these terms are neglected, we are remaining here Vm is equal to Im into Rl, right? Now where I will put this? I will put this value of Vm here. Okay, now I think it is clear. So due to this, what I will be getting? I will be getting PAC. So should I put here only? Yes, that can be. So with this I am getting this, instead of Vm I am putting Im into RL, and solving this completely, what equation I am getting? I am remaining here with Im square, because this Im and this Im square, and this RL I will be writing here. First this 2 into root 2, that is 2 under root 2, and it is RL. Is it okay now? So the PAC is Im square divided by 2 root 2 into RL, right? So after this we can directly put this all value here, where after solving completely we will be getting the equation for transformer utilization factor of the half wave rectifier. Okay, so now let us write this. So transformer utilization factor, which is nothing but the PDC by PAC. So the PDC is this, so that value I can write Im by pi, it's a square, multiplied by load resistor RL. And what is PAC? So this final value I will write. So it is Im square divided by 2 root 2 multiplied by RL. Now I think it is now easy to solve. So this RL will get cancelled, Im square will get cancelled, and what we are finally remaining with? We are remaining with 2 under root 2 divided by pi square. Now you can put the values of this whole thing means value of pi and solve. If you solve this, you will be getting it at 0.287. so this is the actual value. And as we do in case of the in case of efficiency also, if you calculate the efficiency, you will find it is not more than 28.7%. it means that the total transformer utilization factor is even equal to 28% in case of half wave rectifier. So this is the very poor value, because the maximum percentage value can be 100% also. So this shows that transformer is not fully utilized. It means we can say it is very poor value of the transformer utilization factor in case of the half wave rectifier. So this can also be added as one of the limitation of half wave rectifier circuit, that it is not utilizing the transformer to its full value. Okay.